We are next going to consider a conservative holonomic system. And holonomic means that all constraints can be written as a constraint surface, a function of the generalized coordinates and time only, equal to 0. So all of our constraints in a holonomic system will be written as some function f of the generalized coordinates and time equal to 0. We're going to define a generalized, sometimes known as canonical momentum, P sub j, as the partial of the Lagrangian with respect to the time derivative of the jth generalized coordinate. From the Euler-Lagrange equations, we can write that the time derivative of this jth generalized momentum is equal to the partial of the Lagrangian with respect to the jth generalized coordinate. Remember, we're dealing with a conservative system, so this is the version where the right-hand side of the Euler-Lagrange equations is 0, and so these two terms have to match up. This expression is also known as a generalized Newton's second law, again, specifically for conservative holonomic systems. If L is cyclic in Q sub j, that is, if the Lagrangian is independent of the jth generalized coordinate, then the time derivative of the jth generalized momentum will be 0, and so P sub j will be constant. All cyclic variables represent conserved quantities in your system. Another way of saying that is that generalized momenta corresponding to cyclic coordinates are also constants of motion of the system. We can now write the total derivative of the Lagrangian with respect to time as the partial of L with respect to t plus the sum over all of our generalized coordinates of the partial of L with respect to each generalized coordinate times the time derivative of that generalized coordinate plus the partial of L with respect to the time derivative of the generalized coordinates times the second derivative in time of each generalized coordinate. And this part of the expression can be rewritten as the sum of the time derivative of the partial of L with respect to q dot j times q dot j minus the sum over all of our generalized forces multiplied by q dot j. Therefore, the scalar time derivative of the sum of all of the time derivatives of the generalized coordinates times the partial of the Lagrangian with respect to the time derivatives of those generalized coordinates minus the Lagrangian itself is equal to the partial of the Lagrangian in time, negative, plus the sum of all the generalized forces multiplied by all of the time derivatives of the generalized coordinates. From this, we are going to define an energy function, h, of the form the sum of the time derivatives of the generalized coordinates times the partials of the Lagrangian with respect to the time derivatives of the generalized coordinates minus the Lagrangian itself. This means that the time derivative of the energy function is equal to negative the partial of the Lagrangian plus this sum term. If the Lagrangian is independent of time, and if there are no generalized forces, if all of these q sub j's are 0, then and only then is h conserved. This term, this summation of generalized forces times the time derivatives of the generalized coordinates, is sometimes known as the power supply. This is what's going to drive your system along. If there are only time-independent potentials with time-independent constants, then you can demonstrate that this energy function is equal to the total energy, the sum of the kinetic energy plus the potential energy. And this, in particular, is true for the pure n-body gravitational problem. Any number of particles interacting solely through gravity will have an energy function that is equal to the total energy of the system. The Euler-Lagrange equations, just like the scalar equations that we get from applying Newton's second law via linear or angular momentum balance, all of these give us n second-order ordinary differential equations for a system with n generalized coordinates, or n degrees of freedom. We can instead find 2n first-order ODEs, much like what we do to our second-order differential equations when we go to numerically integrate them, but we can directly find 2n first-order ODEs operating in the generalized coordinates and canonical momenta directly. And this gives us what is known as a phase space description of our system, given by QP, the pairs of generalized coordinate and its associated canonical momenta. To do this, we are going to use what is known as a Legendre transformation. So we are going to transform the space Q dot T to the space Q P T. And here we're denoting all of the generalized coordinates and their derivatives and all of the canonical momenta via these vectors that are just collecting up all of the individual pieces. We're going to define a Hamiltonian H that is a function of Q, P, T as the sum of Q dot J times Pj minus the Lagrangian. The total derivative of the Hamiltonian is therefore the sum over all the partials of the Hamiltonian with respect to the generalized coordinates times the total derivatives of the generalized coordinates plus the partial of the Hamiltonian with respect to the canonical momenta times the total derivative of the canonical momenta plus the partial of the Hamiltonian with respect to time times dt. If we consider the total derivative of one term out of the summation that defines our Hamiltonian, we can write that is the ith generalized momentum times dqi dot plus qi dot times dpi minus the total derivative of the Lagrangian, which works out to the partial with respect to qi dot, dqi dot, then the partial with respect to qi times dqi, and the partial of the Lagrangian with respect to time, dt. This can be simplified to, because the ith generalized momentum is the partial of the Lagrangian with respect to qi dot, these terms cancel out. This and this go away, and so all that's left is this term, and this term, and this term. From the Euler-Lagrange equations, negative the partial of the Lagrangian with respect to the ith generalized coordinate is equal to negative the total derivative in time of the partial of the Lagrangian with respect to the time derivative of the ith generalized coordinate plus the ith non-conservative force. And this is exactly our definition of the conjugate momenta. And so this is also equivalent to negative the total derivative in time of the ith generalized momentum plus any non-conservative force acting in the direction of that generalized coordinate. And so we now have a new set of equations known as Hamilton's equations, where the time derivative of the ith generalized coordinate is given by the partial of the Hamiltonian with respect to the ith generalized momentum. The time derivative of the ith generalized momentum is equal to negative the partial of the Hamiltonian with respect to the ith generalized coordinate plus any existing non-conservative force in that coordinate, and negative the partial of the Lagrangian in time is equal to the partial of the Hamiltonian in time. If there are no non-conservative forces, if all of these terms are strictly zero, then the system is known as a Hamiltonian system, and the Hamiltonian is equal to the total energy of the system. In all other cases, the system is non-Hamiltonian, and H is not equal to the total energy.